Hi, I'm Shay, a PhD candidate at Tel Aviv University, and I'll present our work, MonSter, Awakening the Mono in Stereo. Stereo depth estimation is a widely used passive depth estimation method, but it suffers from a few cardinal issues. Our goal in this work is to use Monocular Depth Map, a depth map from a single image, to improve the performance of a stereo depth estimation system. Two of the cardinal issues stereo methods suffer from are inferior accuracy in the very close depth ranges and the need for an extrinsic calibration. So, how can we improve these using monocular images? Let's start with the stereo depth range. The blue and orange curves represent the relative stereo or mono depth estimation error. As each method has lower error in different depth ranges, fusing the depth maps together can improve the overall result. And now for extrinsic calibration. Almost all of the stereo methods assume the input images are rectified and the baseline is measured. In most cases, this is achieved by capturing images of a calibration target, which is a controlled offline process that is usually done once in manufacturing, and is sensitive to physical damage or even temperature changes. We present a method to perform online self-calibration or rectification with the help of the Monocular Depth Map. Our system is comprised of two cameras that serve as a stereo set and is the source for two separate monocular depth maps. We use the left monocular depth map to extend the stereo depth range and the right monocular depth map to calibrate the stereo set. In our experiments, we use two monocular methods, an image-based method that estimates a monocular depth map based on the image itself, and a phase-coded aperture mask method, a method that requires a phase mask in the lens which enables estimating absolute depth map. To fuse the depth maps, we use the Fusion CNN. The Fusion network uses a confidence metric on each network output to create a binary fusion mask. Here is an example of our fusion result. The fused depth map in the right shows a more accurate depth map from each of the stereo and mono methods alone. Overall, we show an improvement of 10% in relative depth error on our generated simulated dataset. For the self-calibration or rectification task, we developed the following method. We start with an unrectified stereo pair images. We train a differentiable projective transformation, or DPT, that learns the transformation needed to rectify the right image. We do it by requiring consistency between the stereo and mono depth maps. We use a pre-trained mono and stereo networks and back-propagate the loss to the DPT block to optimize it. Once the mono and stereo depth maps are consistent, meaning their difference goes to minimum, the DPT is trained and the transformation was found. If the mono depth map is relative, rectification can be achieved, while full calibration is possible with an absolute depth map, like when using the phase-coded base method. We measure the depth estimation error for several methods of self-calibration. Our method achieved the lowest error, as can also be seen qualitatively on the example. Our self-calibration method shows its superiority over other methods on real-world photos as well, like the uncalibrated Kitty dataset. To conclude, we present a novel method to use monocular depth estimation to improve stereo results. We showed how fusion of the depth maps can improve the overall results, and now we can use monocular depth map as a reference for calibration of the stereo camera. For further details, see our paper and please contact us for any questions. Thanks for watching.